Good afternoon, everybody, and welcome to another class on machine learning. Hope you're all doing well. So the last class we discussed on, who can remind us what we discussed in the last class?
Logistic regression.
Logistic regression. Thank you, Vanessa. We discussed on logistic regression. I want us to try and give us the summary of what we taught under logistic regression.
Okay, so I'll just
Okay.
So in the last class we talked about logistic regression, and I remember Prof mentioned how that it is ideal to get the possibility of a categorical data because it is how will I put it now? It is good for binary data like yes or no, positive or negative, when we are working with those kind of data. Yeah, and it works with the sigmoid function. You mentioned that
Yes.
it works with the sigmoid function. What else?
Yes.
Yeah.
Thank you, Mercy. You've done well. Who wants to add to what Mercy has said?
Let me try. So I think we also talk about steps where we say that we have to turn words into number. Then we talked about weighted voting, right? Like step two, after turning them into numbers, then we go ahead, we do weighted voting, which we say that we give weight to words, and then we talked about adding up and squashing into probability. Yeah, and I think that's where the plenty mathematics came in.
Yes. Thank you, Vivian. That is great. So in addition to that, last class, I think we were unable to treat the exercise under logistic regression. So today I'll give a summary of the last class that will cover up for this practical exercise, most if not all. So let's go back to logistic regression. We said that in linguistic, logistic regression is used for text classification. Generally, we use logistic regression to classify. But when it comes to linguistic, that has to do with tests, labels, words, sentences, languages. Then we use logistic regression to classify text. It is used to predict, or let's say model, a categorical outcome, just like Messi mentioned earlier. The categorical outcome in this case must be binary. Logistic regression deals with binary outcome only. In the case of zeros and one, that's where we have the number. For example, we have yes and no converted to 1 and 0. We have a man and woman converted to 1 and 0. That can be in any case as well. Or let's say win or lose converted to 1 or 0. So text classification is about assigning categories. I'm just summarizing what we did on that discourse. So it's about assigning categories to words or a sentence. As the case might be, in the last class, I think Prof used an example of a review sentence to classify the review as either positive or negative. Do you remember? So that's what we call classification, basically. And when it comes to logistic regression, how does it work? So I will give one more example to expand our knowledge on what we did the last time. So you can put this down in your notes, but I will open my board to solve this for us. So let's assume that, let's look at a simple example. Let's suppose you want to classify a sentence. what is the sentence? An example is it's. Let's classify the sentence. It will rain today. This is a sentence, right? So let's assume you want to classify this sentence as to whether this sentence is about weather or not. By weather, I mean W-A-E-A-T-H-E-R. Is this sentence, we all know, literally this sentence is about weather. But let's assume you have a lot of data in real life situations that you have so many texts, or let's say corpus. Corpus is a collection of text, sentences, and all of that. And you have to classify this corpus based on a particular category. You know, you don't have to go through it manually and all of that. But why we are doing this is for you to understand how it works, how we use logistic regression to classify a text. Normally, when we have a large data set, we are going to use a software. And that's why last class, Prof did a practical example on using R to solve this case for us. So we are given a sentence, it will rain today. And we want to classify this based on whether this sentence is about weather or not. Not might be that, is it about something else? But we both know this sentence is talking about weather. So how do we go about it? First thing first, in any analysis, machine learning, we have to start with data, right? But do we have a data for this? I'll give you a sample data that we are going to work with. Let's say we have in our data, remember in data we have different features, right? Let's say we are given these features which are included in our data. Let me use, okay, sunny or sun, as the case may be. This is just an example of a data set, small data set, to help us understand what we are doing. Sunny, cloud. We call these features in logistic regression or in machine learning. Cloud and then rain. Let's say we have all these features. By features, we also mean words. Or let me call them words. Features can also be words. As you can see, these are words that we are dealing with. I remember when it comes to logistic regression, the first thing you need to do, just like we summarized and we discussed in the last class, is that you need to calculate your weighted sum. The weighted sum then goes through the logistic function, also known as the sigmoid function. What is the essence of using the sigmoid function is that it converts the weighted sum into a probability. Then it's the probability that you now decide on using the decision rule, and then you interpret your analysis. So who can remind us of the formula of the weighted sum, like we discussed in the last class? Anybody wants to try?
I don't know if it's what is this. Is 1/1 plus E minus Z. Is it that one?
That's the sigmoid
The
function.
weighted sum. Can I try, please?
Yes, go ahead, please.
Z equals B naught
Yes.
plus B1X1 plus B2X2 plus B3X3 plus and so on.
Yeah. Thank you very much. Is that Vivian Heritage or Mercy?
This is Ibukun.
Ibukun. Thank you, Ibukun. I was asking earlier, is this your first time or perhaps second time in class?
Second time in class.
Second time. Wow, you're welcome.
Thank
So
you.
B naught plus B1X1. Please note, instead of B1, you can also use W1. And I think the last class, Prof used both in the note he gave us. So to make it simpler, let's use W1 for today. W1X1. And because we are having how many features in this data? 3 features, right? 3 words. So we are stopping on W3X3. Please take note. Plus W2X2 plus W3X3. Please, can you unmute? Can you mute yourself? Someone is.
Yes, I wanted to ask a question. That's why.
Okay, please go ahead.
The B naught.
Okay.
It has to be at the beginning always, or it can move. I don't know.
It can be anywhere. You can put it at the last. So far, you know
Okay.
what it means. So far, you
Okay.
know what you're doing. It's the
Okay.
same, right? So the B naught in this case in the intercept. The W1, W2, W3, those are the weights. The weights of each features. And by weights, how do we get that? You'll be given, because when it comes to real life situation whereby you have a large data set, the weights will be trained to be estimated during the training of the data set to be given to you in this case that we are dealing with. And the X1, X2, X3, they are the features. Like I mentioned earlier, features are what was if each of these X1, X2, X3 are binary, it's either 0 or 1, based on whether that particular word is present or absent in the sentence we are trying to classify. What do I mean? Let's take, for example, we are given our intercept B naught to be -1. W1. W1 in this case is referring to the weight of the first word or the weight of the first features. In this case, this is the first word, right? This is the second and this is the third. So the weight of Sonny, or you can put, in a simpler form, you can put W subscript Sonny. Do you get that? So in this case, W1 equals, let's say, -1.5. W2 equals 1, and W3 equals 2. So how then do we obtain the features? These features are between zeros and 1, and sometimes we call them vectors. Vectors of the features. How do we get the vectors of these features? Like I mentioned earlier, depends on whether the particular features is present. So let's say present here is based on the presence or absence of each of these features. So is Sunny, for example, is Sunny present? Yes or no, right? It's either present or absence. Yes, the vector for yes is 1. If it's present, you put 1. If it's absent, you put no. In the statement we are given, it will rain today. Do we have sun in this statement? That's 0. No, right? Do we have cloud? No. But do we have rain? Yes. This is our data set now, in this case. Now let's insert our values into Z, looking for the weighted sum. The weighted sum will now be, what's our P naught? -1 plus what's W1 minus 1.5 multiplied by x1, that's the features for Sunny. The vector feature vectors rather for Sunny, that's 0 plus W2X2. W2 is 1. And X2 is 0 as well. Plus what's W3? 2. And X3 is 1. This if somebody should use the calculator and tell us what do we have as Z. Minus 1.5 multiplied. All this we cancel, right? This is 0. This is 0. Then we have -1 plus 2. Then what do we have? 1. Now this is our weighted sum. After getting the weighted sum, what we need to do next is apply the logistic function. We also call it sigmoid function, which is the, yes, is someone raising my hand? Please go ahead.
Hi, Kafaya. Sorry, I didn't
Yeah.
get how you were able to get the W1 equals to 1.5. That's where I lost it.
That's where I also lost it though. Was just trying-
W1 equals 1.5. Yeah,
Yes,
I was
how did you
explaining
get
that
it?
the weights, those are the weights of each of these features, and they will be given to you. You are not to estimate them. Those values are given. And I also mentioned that when it comes to real life situations, when you have a large data set, this weight will be obtained while training the data set by the whatever software you want to use. So in this case, it's just for you to understand the basic. These values are given. Is that clear? Is it?
Yeah, thank you.
I'm sorry, let me circle back. You're saying that B naught would be supplied.
Yes, that's the intercept.
Okay.
All right. So next thing we want to get the probability value. This will allow us to decide on whether the statement is a whether statement or not by using the decision rule. And you can't apply the decision rule until you calculate the probability. And that's what the logistic function does for us. Then the formula is 1 over, like we mentioned earlier, 1 over 1 plus exponential minus z. The z in this case is what we just calculated. That's the weighted sum. So we have 1 over 1 plus exponential minus 1. So if you calculate this, you get 0.731. Now, this is our probability. Now, what's next? If you go back to our course manual, then the next thing is to apply the decision rule. What's the decision rule? It said if, okay, I think Prof shared another note on, who can tell us what the decision rule is? Who wants to give us the decision rule? Give us the decision rule and then apply it in this case. Anybody?
I want to try, please.
All right, please go ahead.
Okay. The decision rule is if P is greater than or less than 0.5, it is positive.
Yes.
And if it is less than 0.5, it means it is
It means
negative.
what?
It's
Negative.
negative. Yes.
Yes, thank you. So what do you mean by positive and negative in this case? Remember, we want to classify whether the sentence is about whether or not, or let's say it's a whether sentence or not. So how do you classify this sentence now? Yes, you are right, Ibukun. You want to give it a try.
No.
Okay.
Let me try.
All right, please go ahead.
Okay, so I think if the probability is at 0.7, which means it is very, very close to 1,
Yes.
where one is positive, right? Ibukun, that's the
Yes.
rule.
Yes,
So
yes.
that means it will rain that day. That means the probability is high. Yeah, that it will rain that day.
Yes, you're right. But in this case, we are not talking about what will happen. We are only interested in the sentence. Is it a whether sentence or not? We want to classify this. And since our P is greater than 0.5, right? How do we classify this sentence? Is it as whether or not?
As
We
weather.
classify
As
Exactly.
whether.
So
Well,
since B is greater than 0.5, that's the decision rule in this case now. The sentence would be classified as whether. Is that clear? So since we have done with classifying, I think by now this broaden your understanding of what we did the last class. In summary, when you are dealing with logistic regression, remember you are dealing with features. Those are words, and the features are whether each of those features is present in the given statement or not. That's 1 or 0. Then you calculate the model weight or the weighted sum, which you then apply in the sigmoid function to obtain the probability, which you then apply the decision rule on, and then you interpret your statement or your probability. In this case, we classify the sentence as a whether sentence. So is there any question based on this?
Excuse me.
Okay.
All right. It means that the kind of problem we are solving will determine in the final analysis the decision rule. In the last class, I remember that it was positive or negative. That was the decision rule. But today we are talking about whether it is
Yeah.
classified as a whether or not.
Yeah, in the last class, we were talking about whether the review is a positive review or a negative review. And that's why the decision rule is such. Do you get that? The decision rule will be based on your question, what you are trying to achieve, or let me call it hypothesis. Is this statement a whether statement or not? Then the decision rule will tell you this is a whether statement or this is not. Is this review a positive review or a negative review? Then the decision rule will tell you this statement is a positive review or a negative review. Do you get that, Ibukun?
I do now. Thank you.
Yeah, that's good. So I think with this, we will be able to answer the exercise questions on our own. And please do well to practice them at home.
I'm sorry, very quickly. On
All right.
your white board, P equals 1/1 plus
what number did you write or letter did you write beneath the 1?
Over 1 plus exponential minus z.
Minus z.
That's the formula for the logistic function.
Right. An
More
E.
important. What do you say?
So that's an E.
Yeah, E. It stands for exponential. It's a natural exponential. Yeah. Exponential. So when you press this on your calculator, exponential minus 1, you get the answer. 1 over exponential. Exponential minus 1 as a value. The calculator will do that for you. And then you substitute for that. Do you get that?
Yes, I do. Thank you.
All right, you're welcome. So I think with this, we are good to go on logistic regression. So for today's class, we'll be moving on to word embeddings and natural language models, which I will hand over to Ms. Oni to take this part. Thank you.
Okay, thank you, Ms. Kafaya. Good evening, everyone. I will be sharing my screen now. Okay. So I want to believe that we can see my screen. All right, so in today's class, we are going to be talking about word embedding and neural language models. So, we've been talking about machine learning in this course, and just like Mrs. Kafayat recap, last week we talked about logistics regression, but today we are going to be talking about another concept again, and that is word embeddings. So first of all, before we go into the definition, I know that we have emphasized it in this class before that we could have words, but just a particular word rather, and they can mean different things. I think we've taken such examples before. Can anyone help us out? A word that has maybe 2 different meanings.
Bank.
Beautiful, bank. In fact, that's the example I can still recall. Bank. So we could have bank as in river bank. We could have bank as like a financial institution and all of that. So we have to understand the importance of contextual meaning when we are, working on language, texts, and all of that. It is very, very, very important for us to be able to interpret whatever we're doing in context. And that's one of the things that is bringing us to today's topic. So one of the things that should, be in our mind as we are taking to this class is that how do machines understand language? What do I mean by that? If you're chatting on your WhatsApp, sometimes it may be based on the fact that you have always been saying that statement. You've always been typing that particular statement. Then by default, once you type, in fact, it happened to me, it was this morning. The moment I just typed Mr. on my WhatsApp trying to send a message to my boss, I just said Mr. Then it brought suggestions of 3 different Mr.'s that I always, after I've said Mr., the next word. So it gave me 3 different suggestions of the people around me that I always use Mr. this, Mr. that for. Now, how do that work? That's one of the things that we want to, introduce today, so that we can understand how machines are able to predict your next word and, like 70%, 80% of those times, the machine gets it correctly, and you're like, exactly, this is what I'm looking for. Sometimes it could even be spelling it. And after you've written maybe CRO, then it gives you suggestions of what could follow, something like that. So we have here that word embeddings are special ways of representing words as dense vectors in numerical space. And then that each word gets a list of numbers that capture its meaning based on how it appears in real text. So I want us to understand that whenever we are talking about word embedding, let's have it in mind that there is something that we call a space. And what we want to check is how close are those words are to each other in that space. How close are those words? The space is termed like vector space. So I'm going to be sharing my whiteboard, and I'm just going to draw like a 2D graph. Maybe it's going to help our understanding better. Okay. So let's assume we have this graph. Yes, this is a two-dimensional graph because we can only see the y-axis and the x-axis. Yes, this is the x-axis, and then this is the y-axis. So, for example, if you plot a word, like if you, in your vector space, let's assume we have a word king, as it is in our material. We have king. Let's assume we have the word king. And we have maybe man. And then we have woman. And we have woman. Yes. And this is your space. Assuming this is your space. So it is expected that, if you have king here, your man can be somewhere around this king. If this is king and this is man, and this is man, maybe your woman will be opposite of where the man is, and it still won't be close to the king. So maybe the woman will be negative. If we are talking about gender, let's assume this is where the woman is, opposite of where the man is. Now, you see what I'm trying to draw. Now, what we have right now is a vector space, and we can see how our words are close to each other. So you will see, if I'm to draw a distance, you will see that man and king are closer than woman and king. You will see that they are closer. Another example again is, let me show us another example. Another example that we can have is, okay. Okay, so let's assume we have happy. We have a word happy. Happy would have its own, numerical space, numerical representations. Then if we have the word excited, excited, I think it's C. We have the word excited. So let's assume happy has its numerical representations as maybe 0.7, 0.7, 0.59, 0.59. Then maybe we have 0.9. Yes, in the context of feelings. Yeah, should I say feelings or emotion? I don't know how to. Excited will also have, based on your trained model, would have a numerical representation very close to happy. So you might be having something like 0.69. If this is 0.7, maybe 0.69. Maybe 0.61. Maybe 0.87. Something very close. So if I were to plot my graph on this pace, if I were to plot it, my happy might be found here. This might be my happy. Then maybe somewhere close, based on the numerical representation, somewhere close, you will find the word excited as well. You find the word excited. But let's assume that we have the word angry. Let's assume that we have the word angry. Say angry is here. Angry. So angry also would have its own numerical representations. And it will be far from happy and excited. In fact, probably at the other hand, because it is a negative word. So sometimes when you are now looking for synonym of a word and you are about to write happy or something, then your machine can suggest to you something related. Why? Because those words are close together in the model. Your angry might be maybe somewhere around there, somewhere very negative, so very opposite of the other words. So your angry might be somewhere around there. So depending on your context, it depends on your context. But this is what, when we are talking about word embedding, this is like what we are talking about. There is a popular example, a popular calculation. I think is it Google now that used the research on it, and then it's now like a well-known example. Then they give us this first example I mentioned about king, and then you see something, even if you check online, you see something like king, let my K be king minus man plus woman. The king will have its own numerical representation. Don't forget, the man will also have its own numerical representation, same thing with the woman. And then you would have, if you check it, you will see something like equals to queen. Equals to queen. You remember, is it in one of these reasoning course or subjects in primary school days, they will say man is to king as woman is to queen. You know, all of those trainings, these are the kind of things that we were training our minds to know. We were training our minds to know, such that we know that, okay, based on the relationship between these two words, then this other word, if I'm to also replicate it, then I just have to follow the relationship between these two words and replicate it with the other pair of words. Another example is if I say, okay, maybe somebody will help me out here. If I say apple, okay, apple, then I have fruit, then I plus, let's say I have car. So can somebody probably just give me a suggestion of what my answer should be like? Hello? Hello?
We are here.
Okay, if you are here, then I used an example of the king minus man plus woman to give us queen. Then I'm asking for this other example, saying if I have apple minus fruit, just check the relationship between apple and fruit. Then if I now have car, then what's likely to be your suggestion if you were a machine? What is the relationship between apple and fruit?
I think they belong to the same class. They are both fruits.
Yeah, it's not. Should we even say they belong to the same class, or apple is an example of a fruit?
Yes.
So if I now have the word car, and I'm telling you that based on the relationship of apple and fruit, and then we have the word car, what's your next suggestion going to be like for car? If apple is a type of fruit.
Like vehicle?
Like what?
Vehicle.
No, I wouldn't suggest that. Vehicle also would be a close word, but I'm sure based on this relationship, there will be words that are closer. Fruit, apple is a type of fruit. That means you'll be looking for type of cars. I'll be expecting responses like Camry, Toyota, Tesla. Do you get it?
Yeah, I think so.
Okay.
Okay. Okay, let's consider another example. Let's say we have walking. We have walking, like somebody is walking. We have walking. We have walk. Walk. Then we now have swim. So what's your next suggestion going to be like?
Swimming.
Swimming. Why? Because you have observed the relationship between these two here, and you were able to make the next prediction of the next word I'm going to write. That's the same way some of these gadgets or devices suggest the next words to us. And when we are talking about word embeddings, that's what we are talking about. There are different other examples. It could be country. It could be maybe you say it's a state, then the capital, then another state. It could be countries and their capital, then another country and another capital. Then you have to suggest the name. So that's what we call it word embedding, trying to look at their relationship. How close are they to each other? And you see these signs here, these negative signs and these positive signs, they are not just for what's that word now? They're not just for design. you can actually calculate them. If you have if you see the numeric, okay, for example, this. So if you were to look for, in a space where you have a lot of words, and you are to check, okay, maybe happy minus excited or something, by the time you do all of your calculations in your numerical representations, then you now go and check the words that are close to what your calculation is like. For example, if my king, let me use the second one. If my king has this kind of representation, 0.8, 0.5, all of these numbers actually have there is a way to understand them. Maybe I would still get there. They are not just figures that you will just determine by yourself. Although probably for the sake of exams, maybe such might be given, and hypothetical values might be given to you. But what have been trained by different bodies. Google have their model, Facebook have models, all of these AI organizations have models that they've built to train. They've trained models to be able to give us some of these things. Then let's say we have man to be 0.7. Then we have 0.3. This is just on a 3-dimensional space. This thing I drew for us the other time was a 2-dimensional space, but let's assume this is on a 3-dimensional space. 2. And then we now have woman as 0.6, then maybe 0.6 again, then 0.4. Then you have to use the model developed by Google. Then what you're going to be having, your next word is supposed to come as a result of K minus M plus W. So you're supposed to have something like, so we pick it one after the other. We do for the first one, that would be 0.8 minus 0.7 plus 0.6. We can do this together. If you're following and you want to be sure you're getting it, you can omit and you can probably tell me the next figure I'm supposed to write. Then after we're done with the first one, you pick the second one, just separate it to a comma. Then you have 0.5 minus 0.4
minus 0.6.
It should be plus.
Plus,
0.6, yes. Plus 0.6. Then the last dimension, we have 0.3 minus 0.2 plus 0.4. So at the end of the day, for the next word, we are going to be having 0.8 minus 0.7, that's 0.1, plus 0.6, that's 0.7. 0.7, comma, 0.5 minus 0.4, that's 0.1, plus 0.6, that's another 0.7. Then 0.3 minus 0.2, that's 0.1, plus 0.4, that's 0.5. So you will now have to, your machine rather, the machine will then check which of the words have this kind of, is very close to this numerical representation, and most likely it will be maybe something, maybe queen. That's how we got about that king minus man plus woman equals queen and other examples. Because by the time you have your numerical, your vector space, and you check those words, you would see that it is very close. you see that this dimension is close to king, this dimension is close to being a woman, this dimension is also close to being a woman. All of these dimensions that I'm talking about, you can also think of it like features, which could be maybe gender, it could be gender here, it could be maybe age, it could be maybe skin color, it could be, you understand? So all of these ones are based on features. In fact, you can have your document, your corpus, and you have like maybe 300 dimensions. That's, you are checking each of your words based on 300 features. So at those times, you won't be having just this 3. You are expected to be having like 300 figures. That's where machine comes in. And that's how our machines were trained to be able to make almost accurate predictions of what your next word will be like based on the context of what you're saying. Based on the context of what you're saying. Let's go back to our materials. Abandon that for a while. Let's go back to our materials and see what we have. So let's go to 5.2. Why do we need word embedding? I think I've kind of mentioned that there are traditional methods. Traditional methods are the ones that we count with their frequency. We do word frequency and we count it. How many words, how many apple are in this sentence? How many colors are in this sentence? All of those ones. But it has been realized over time that they sometimes do not capture the meaning of the word in its context. So your interpretation is just based out of context. Your interpretation is just based out of context. For example, there was a work I did, a personal work I did, and it was part of the recommendation that I made because, okay, it was sentiment analysis. At the end of the day, the algorithm, the model just, gave me each of those words and their supposed sentiments based on what had already been programmed in the dictionary. For example, it is known that when you say happy is a positive sentiment, even if you talk about the emotion, you say maybe joy, all of that. If you say the word love, you want to think about it as positive. If you say sad, you want to think about it as negative. Somebody is trying to join. Okay, if you say sad, you want to think about it as negative. But sometimes there are words that, fine, it is sad, but that might not be what the meaning of that sentence is actually saying. For example, maybe a sentence like, this movie is far from being sad. Models like one-hot encoding and all of these traditional methods will just pick the sad and capitalize on it as being a negative word or negative statement. That's the reason why we have to go further to know word embedding, to know how word embeddings, how it comes to place, and how it can help us solve interpretation of words out of its context. So please, when you are asked the question of why do you think word embedding is very important, please understand the fact that there are so many models, so many methods that do not interpret words in their context. So we have here that words with similar meanings have vectors that are close together. The vectors are what I showed you, the numerical figures are what I've shown you. So at the end of the day, you see that they are very close to each other. Their distance are very close. You know that those words have similar meanings. Then they capture both semantic similarity and syntactic relationship. I think Ibukun is fighting with a network. And syntactic relationship. So those are the reasons why we need to understand word embeddings. And for my chapter, for my 5.3, we mentioned that For example, when we talk about similar words like king and queen, we mentioned it, walking and walk, swimming and swim, apple and fruit, maybe Italy and Rome, Nigeria and Abuja. Words like that they have tendency of being close together in when we talk about distance in our vector space. When we talk about distance, they have tendency of being closer to each other. Look at this example here. Our material says that apple and orange are closer than when you see apple and chair. So chair will be in another space entirely. Chair will be in another Euclidean space entirely. Please, I hope the terms are not confusing us. Please, if you are confused at any point, please feel free to interrupt me so that I can recap whatever I've said. So, like, what I'm saying is that if my if apple and orange are here, you will find a word like chair maybe somewhere here or somewhere here. So at the end of the day, when the machine, your computer, looks at it, and you mention this, it automatically knows that maybe based on the data that you have fed it in, it automatically knows that the next word you are likely to say, based on what others have said over time, is this, and not this one that is very far to it. Okay. I hope that is gotten.
I believe we understand.
Sorry, can you go back a bit? My network messed up.
I didn't get that, Ibuko.
Please, can you go back a bit? My network messed up. I couldn't get the rest.
Okay, which part were you lost? Let me see if we've not gone too far. If we've gone too far, you just have to watch the video. But which part were you lost?
When you were explaining the values for the key men and women.
When we were explaining, did you see how we calculated this?
Yes. It was after.
Okay, that means it might be at the material part. So I was explaining the reason why we need to study word embedding, why word embedding is very important. And then I was explaining to us that I've done a work before where I've done sentiment analysis work, and it was part of my recommendation that other models should be looked because those particular algorithms did not capture the meaning of the word in context, and they can be very detrimental because you might mean something else entirely. You might be talking about something else entirely. But based on, for example, the bank that was it heritage I mentioned it earlier. For example, the bank, we'll be talking about river, water, and all of that. But maybe the bank that has been programmed into this kind of method, traditional method, is financial institution. So those kind of mix up can happen. And that's why we have to study word embedding. Then we just talked about other examples that we've even talked about initially. So we just reiterate on that. All right, so the next thing again now is that we have different word embedding models. We have different word embedding models, but the common ones are the word to vex and globe. How do I even pronounce it? It means global vector. So it sounds like globe or globe. I don't even know, but it means global vector. And then the word to vex means word to vector. It means word to vector. Let me draw a chart for us so that we are not confused with how this thing actually, the trend they follow. Okay. So let's assume we have the root word embedding. Okay, let me create another slide. So let's say we have word embedding. Word embedding. Then let's assume what embedding is divided into 2. So we have the count method, the method of what embedding is. So we have the count or the frequency. The count or frequency. And then at the other end, we have deep learning trained models. We have the deep learning trained models. That's where our the machine learning aspect comes in. So we have the deep learning. So deep learning models. Now, the deep learning models are very good with accuracy. The other one I described the other time, where you just try to count how many words is this in your corpus, how many, those ones are count of frequency, you know that. But what embedding that we are talking about today is the one under deep learning trained models. And even that one is where we have the word to vec. We have the word to vec. Sorry, we have the word to vec. We have the glove. I'm not sure how to pronounce that thing. Global vector. We have FastText. We have FastText too, so that we are not confused about how these things flow. So we have FastText too. Those are the most common ones. Now, the word to vec, we have two approaches that can be used for the word to vec. We have the SIBO and we have the skipgram. We have the SIBO and the skipgram. The SIBO is the SIBO is a continuous bag of words. Who can tell me what do we mean by bag of words? Because I think we have come across it in this class before.
No, not in this class.
It wasn't in this class. Okay, maybe it was the other.
Yeah.
Okay, so we'll get there. So then we have the skip. Then we have the skip ground. Okay, so the word to vec generally, it uses neural network model to learn word association from a large corpus of text. And one of the things that it does for you, just like I've explained in the introduction, is that it suggests additional words for even partial sentences that you have not completed. It will suggest the words for you. So that's one of the things that word to vec does. And I feel that our introduction, even before now, has covered some part of the word to vec, but I will just have to reiterate it again so that we can know that that is what our word to vec is actually doing. So the explanation I made about say apple, fruit, car, and Camry, king, man, woman, and queen. All of those ones, using word to vec, supplies such answers. It's those kind of model, a word to vec model, are the ones that helps to supply those kind of answers. Okay, let's go to a practical example. For example, now we have 3 sentences. Maybe I drank coffee this morning. He skipped tea while reading. She ordered maybe coffee or what other drink do we know? Or let's say she ordered a drink from the cafe. Now we have 4, how many words? Okay, about 3 or 4 words. We have the coffee, we have tea, we have drinks, we have maybe cafe. So just like I've explained while I was introducing, all of these words would have their own numerical representations. They have their own numerical representations. And how did we get to them having numerical representation? I explained it the other time. I explained the features. I explained features representation that in our words, in our maybe corpus or document, you have the features you are examining. For example, gender, food, drinks, and all of that. So you have them. Now, this coffee now, you would have to examine, is it a drink? Maybe I will even have to remove that word drink. Is it a drink? Is it fashion? Is it fashion? Is it place? Is it place? Now, if coffee is a drink, the kind of number that will be attached to it will be high. Maybe something like 0.9, maybe 0.92, because it is. If it is can coffee be fashion? Can coffee be fashion? So if it can't be fashion, or it might not be, because we are not entirely sure, you might have something like 0.01, something very minute, because such probability might exist. Is it a place? Maybe there is a particular place that they call coffee, you might not know. So maybe you have something like 0.23. For tea, comparing tea with drink, you might have something like 0. Maybe 94, sorry, maybe 91. Passion might also be very small, maybe 0.02. Place, you don't know, maybe 0.11, something like that. Then I said I was going to eradicate this keyword drink. Then cafe. Then when we talk about cafe can be close to drink. So maybe 0. Let's say 72. Cafe fashion, well, I'm not sure. Maybe 0.3. Then being a place, maybe 0.9, maybe 0.91. Now, just like I've explained earlier, this is just reiterating what we have and what we have learned. Does each category make up one? No. We are not, the categories are not targeting on being added up to one at all. It is just does each category make up 1 or all equal to 1? No, we are not summing them up in that regard. They are measuring different things. They are different feature representations. Do you understand? They are different feature representations. So, in this kind of situation, okay,
My network was.
okay.
So I'm asking if they are all equal to 1 or each one is 1. You get, so when we're rating each one, are we giving it like, for the drink now you use 0.9, 0.01, 0.2. So all
Okay.
together, are we measuring it as 1? Or each one has 1 point? Say out of 1, I can decide to give drink coffee under drink 1, give fashion 0.9, give play 0.8, that kind of thing.
Okay, I get your point now. Yes, you are very correct. We are measuring them based on 1. We are not summing them up to the 1, but is under the rate of -1 to 1. So the -1 sometimes being the negative of those words. For example, the king and the queen. Now, the relationship between them, if you are talking about gender, based on that feature, gender, will be positive and negative. So it's always between -1 to 1. So when you have something like 0.997, 0.92, you know that it's very close to that feature. Do you understand now?
Yes, thank you very much.
All right.
I don't understand, please. I thought you said the values are already existing, that there are
I can't hear you.
I thought you said the values are already in existence. The values assigned to features. Are we the one that will assign values to them?
No, you are not the ones assigning. No. This is for the sake of manual calculation and for exam purpose. Models are being trained based on billions of data, billions of corpus. So models are being trained for this word to vec. You just have to, even if it is on your R, I think we are going to have a practical example on R after my session. Models have already been trained, but you need to understand how it actually works so that it doesn't look like magic. So these are hypothetical, but even if they are hypothetical, we still need to stick within the range. Ibukun, do you understand now?
I do, thank you.
Oh, okay. So that is the when we talk about what to vec, that's what we are talking about. So in those kind of situations, when you want to predict, you would know the words that are close to themselves, and that might likely be the next suggestion. All right. So for your SIBO, it's actually sometimes pronounced as SIBO. That's the continuous bag of words. Just like I said, it's another model from the word to vec framework, and you can use it to don't forget that it's still under word to vec, but it's just different commands, different program. So it also predicts the target word from its surrounding context. So if you check our material here, we have, you see, what to vec, it learns embedding using context. I've established that either predicting a word from its neighbor, that's SIBO, or predicting neighbors from a word, that's keep ground. Both of them are used as word to vec models. They are both word to vec models. They are just different approach, but you are aiming at the same output. So just like I said, word to vec is very efficient and is most times used when you want to predict similar in meaning words. All right. Okay, the other one is the global vector. That global vector is used for co-occurrence count to learn embeddings. Co-occurrence count to learn embeddings. And Okay, let me just give us this example of co-occurrence. I think I have to write again. Okay, so let's assume we have a table of, so we have, let's say we have COVID. We have COVID. We have hospital. We have hospital. We say we have death. Let's say we have love. Let's say we have love. Let's say we have maybe food. Now, in my head, actually, because writing is very difficult, I'm supposed to actually write the sentence. So let's assume I have 2 or 3 sentences. Let one sentence be, she loves food. Let another sentence be, can somebody use either COVID and hospital, or COVID and death, or hospital and death in a sentence, or if you can combine the 3? Let me try and write our sentence.
He discovered that he had COVID, went to the hospital and died in the hospital.
Okay, but that's quite long, but I hope we will be able to remember that sentence because we are going to be using it. So let's say she loves food. That's the first sentence. Then the other one is, she discovered she has COVID, went to the hospital and died there. So maybe to be on the safe side, let's use died. Died. Now, here as well, we are going to have the same set of words. So we are going to have COVID. We are going to have hospital. We are going to have died. We are going to have love. We are going to have food. Oh, I wish this sentence would have actually contained. Okay, no, I'm going to change something. I wish some of those sentences have words that are overlapping. So let me say, let's just have 8 here, such that we can have something like, I hate hospitals. Such that we can have something like, I hate hospitals. So, okay, I don't need food anymore. So if we are going to use the global vector concept, don't forget, this is just a concept. Now, if you are going to use the global concept, so you look at your sentences and then you pick it one after the other. Okay, the first sentence is, she discovered she had COVID. In fact, in that sentence, we are supposed to have a large group of words. Discovered is a word, had is a word, COVID is a word, went is a word, to the hospital, to the hospital is a word. We are supposed to pick it one after the other. Then if we are going to achieve that, if we were able to achieve that, then what you now do is, okay, after COVID, the next word that came after it, was it hospital? If yes, maybe you assign it the figure 2. If no, maybe 0. After COVID, the next word or the word preceding it, is it died? That's why it is co-occurrence. Is it died? Did they occur together at any point? Do you understand? Then COVID 8, are they occurring together? If it's 0, it will be 0. If it's 2, it depends on how you number it. It could even be in decimals. Then you go to the next word again. This is hospital and COVID. Okay, go ahead. Go ahead.
So you know that we have hospital and then we have died there. Which there in that sentence is replacing hospital? Would it count in this case?
Can you repeat your
Or
question?
did you get my question?
No, I don't think so.
So in that sentence, we have he died there, right?
Yes, and idea, yeah.
Yeah, that there in that sentence is replacing the hospital. It simply means he died in the hospital, right?
Yes.
So I'm asking, would it be, in this case, can we use that hospital or died came after hospital? In this case, would that there, be classified as hospital?
Well, to the best of my knowledge, the global vector might not be able to classify the there as hospital, but the FastText should be able to classify as hospital. The FastText is the third one. Let me show you the screen. Is the third model that we have in our notes. So undo subword information so it can guess embeddings for unseen words. Don't forget that we are raising 3 different models, and at some point one can handle some things better than the other. For example, for the FastText, when we talk about maybe house and from the house, in the house, if we are going to change from the house to Yoruba, sorry, what is it going to be? Just that phrase, from the house. Anybody from the house? Anybody from the house? If you want to interpret it in Yoruba.
People should talk now.
Láti
What do you say, Ibukun?
láti ilé.
Láti ilé. What about in the house?
Nínú ilé.
Nínú ilé. Okay. When I was working on something like this, I was even thinking from the house. Are they even different? From the house, láti inú ilé, nínú ilé. But that's the aspect that FastText handles. It helps us to, know the words that are written in different ways, but that they have the same or similar meaning. It helps us to differentiate them. So that's why I'm saying that the global vector might not be able to, because that model focuses on word co-occurrence, but the FastText might be able to handle those kind of technicalities of, do you mean the same thing? Are they talking about the same thing? So that's that. I wish I would be able to show us the cosine similarity, how to calculate the cosine similarity, but I feel that might be a bit too much for us. That's what I feel, and it's not in our material. So I think we can, skip that. So if we go to the neural language model, we have that a language model predicts the next word in a sequence. What this section is just trying to, bring to our notice is that all of these, the word 2vec, the global vector, the FastText, they are products of neural network. I wish you have a bit of understanding of neural network, but you know, when we talk about neural network, from the word neural, you know that we are talking about neurons, and if we are relating it to brain, we are talking about how our brain works. Then if we bring it down to machine, we are trying to say, okay, how will the machine work like human? And then there are different type of neural network. We have the artificial neural network, we have the recurrent neural network, that's RNN. We have the feed forward and all of that. So just like the topic is explaining to us, this chapter is to introduce us to how the the human brain is supposed to work, which is now being modeled by machines. Machines are now emulating how our brain will work, how we were trained to be able to know that, okay, if you are reading this word, you don't have to look at your notes completely to know, to be able to capture the next few words in that sentence. So this chapter is just introducing us to that, and then we will see that examples. They're predicting math after the cat sat on the mat. Also, generating whole sentences that sound natural. Those are the functions of neural language models. And just like we have said the other time, all of these word-to-vec, global vector, all the word embeddings techniques make up having a correct neural language models. So we have to put that in our minds. Then we have the 5.6 section that says, how do we use word embeddings? How do we use word embeddings? So in natural language processing task, we often train or load a pre-trained embeddings. Now, just like I said, the word-to-vec and the global vector embeddings are pre-trained models. It has already been trained before now. I just have to give us an idea of an overview of how it was trained. So you will train a model, or you will use a pre-trained model, which is in our R manual. Then we will convert the words in our text to vector form. Then we will feed these vectors into machine learning or deep learning models, as it has been shown in our 5.8. Just like I mentioned, one famous example shows how embedding captures relationship. And then we can see this is a very famous example. I think it was generated by Google, just like I said. All right, somebody's hand is up. Oh, no, nobody's hand is up. All right. Okay, so we are left with the R. But we will probably be taking that one next week. But we just have to understand. I would implore us to, implore us to practice ahead of the class the R codes. If you're having difficulties, let's talk. Then maybe in the next class we are going to do it together. So the steps have been stated here. The first thing you do is to load your package. The next thing is to create example sentences, just like you have here. Don't forget that in real life, you are going to be faced with lot of corpus, like very, very, very large corpus. So this is just an example. Then you will train the word embeddings using this. I told us earlier that it's already there, but you just have to have an understanding of how it works. Then you check the similarity, you visualize. That's where you will be able to draw the chart to see how close some of the words are to each other. And then you'll be able to probably make your conclusion based on that. So the assignment you are going to be giving us, fine, it's not really an assignment that you would submit, but that we would wish for you to try before next Thursday. is to try and run the R codes. So run the R codes. If you're having any issue, we are going to work with you on the group, and if you have to change it, if the issue is so much that you might not be able to clearly state it, we might talk on that in the next class. So probably, except if Prof says otherwise, we are going to be starting with the R codes in the next class. Okay, so I think that's all for today. Do we have questions?
Sorry, because I'm just joining. I don't know about the R package and installation.
Okay. So you first of all, if you know, you can unmute your mic. First of all, you don't have the R package, right? There's no way.
All right. Yes, I don't have it.
You don't have. Okay, so I'm going to send the link where you can download the R package. I'm going to send it to the group. You're on the WhatsApp group, right?
I am.
Are you there?
I've been added.
You've been added. Okay, so I'm going to send the link. You're going to install both the R and the R Studio. These two apps. So when you want to install, you will install the R first, then you install the R Studio. Once you have that one running, then I think you have done like half of the step. Then the next thing is for you to familiarize yourself with the R interface, and I'm sure any of your colleagues might be able to, explain some facts, some things to you there.
All right. Thank you.
You're welcome. Any other question? All right. So I'm sure some of us, everything is not in the class. Maybe Vivian will be very happy that we are ending the class very early today. Okay. All right. So if there are no other questions, let's have a semi-night rest and see you next Tuesday and next Thursday for this course.
Thank you. Have a nice time.
Thank you so much.
You're welcome.
Sorry, please, honey. As Ibukun doesn't have the R yet, we should be able to submit the assignments for next week.
Which of the assignments?
We have assignments though for quantitative methods.
Is it the R assignment?
Yes.
If the assignment is due 6th.
26, yes, it's next week. Hi, Ibuko, you might have to watch the lecture 3. I don't know if she's still here.
I think she's there.
I'm here.
Yeah, that lecture 3 on quantitative methods, because the assignment is due on 26th.
Oh. Wow. All right. I will try my best.
Just try your best and ensure that you submit something, please.
Okay.
All right.
Okay.
All right. Thank you.
All right.
Bye-bye.
Yeah. Good night.